Hello everyone, and welcome to this online session of the LIFEsim tutorial. So this tutorial was originally presented at the Life Science Team meeting in Berlin in September of 2023. And the idea is that we record it now again. So the people who could not participate there also have a reference for this. Before we start, my name is Philipp Huber. And also Felix Dannert is in this session. We are both PhD students at the Exoplanets and Habitability Group of Sascha Quanz at ETH Zürich, and we both work on LIFEsim. Okay, so to give you a short overview of what you can expect in this video, we are going to start with a short introduction to LIFEsim, followed by a hands-on session. This will be in the form of a Google Colab file. You will get the link in a moment, or hopefully it's also in the description of this video. And then we will close with a short conclusion. So the goal of this session is that all of you have an understanding what LIFEsim is and how it works on a high level, and that you understand what can be done with it and what cannot be done with it. Also, we hope that you, after this, feel comfortable to use LIFEsim for your use cases, and also that you have a reference for future questions. In particular, the goals are also not that you know everything about LIFEsim, and also not that you have a detailed understanding of how it works, and also not that you have it installed on your personal computer. There are instructions for how you can do this online, which we will show again at the end of this presentation. Okay, first of all, what is LIFEsim? Just that we are all on the same page. LIFEsim is a publicly available Python package to simulate an observation with life, and it should help the life community evaluate what kind of questions could be answered with the life observatory. So here you can see a screenshot of the life documentation page. We will show the link to this page at the end of this presentation. Now, LIFEsim started out back in 2018 when Sascha Quanz and Jens Kammerer created a first tool that was able to calculate basic yield estimates for the life observatory. This tool was then extended during the master thesis of Emile Fontanet, and we had the first version of LIFEsim that also included the ferrometric calculations after the master thesis of Maurice Ottiger. Then in 2021, Felix Dannert also spent his master's thesis refactoring and extending LIFEsim, and also created the first publicly available version of it. This was also the time where Felix officially took over the lead of LIFEsim, and now since then, not a lot has happened to LIFEsim. There have been a couple of student projects, but none of the extensions made by the students has made it to the main LIFEsim branch yet. Now for this year, it is planned that Felix moves on to other projects and that I will take over the lead of LIFEsim in the life community. More about the future plans regarding LIFEsim at the end of this session. Let's now have a look at the inputs and outputs of LIFEsim. So LIFEsim takes several input parameters. First of all, we have instrumental parameters like mirror size or spectral resolution and so on. And then we also have certain astrophysical parameters, for example, the level of exozodiacal light. We also have exoplanetary inputs, what we call them here. For example, you can input a catalog of an exoplanet population, or you can also input a planet spectrum directly. With this, LIFEsim then basically outputs the signal and noise per spectral bin, and this information can then be used in the next step to calculate yields, or also simulate noise on spectra that you could expect after an observation with life. But more on these two examples later. Let's also have a more detailed look at the workflow of LIFEsim. So again, we start with several inputs, for example, the array architecture. So this is actually hard-coded in LIFEsim. We currently assume the MIX configuration for the collectors and 4 apertures. You can, however, choose the aperture diameter, spectral resolution, exosody level, and also you have the option to input a spectrum or a population catalog, as I mentioned before. With this information, LIFEsim then basically calculates these kinds of transmission maps. And with these transmission maps, it then calculates the photon rates for the different sources. So the photon rate of the planet is what makes up the signal in the end. And then we have several astrophysical sources that contribute to the noise of the observation. This step here, or these two steps here in the centers, are then repeated for each wavelength bin. And once this loop is finished, we basically have the signal and noise per spectral bin as an output. And at this point, we should mention that LIFEsim does include certain noise terms. However, it does not yet include systematic and instrumental noise. There are three main use cases of LIFEsim. First of all, we can use it to generate these noisy spectra that I have mentioned before. So we basically input a spectrum, and then as an output, we get the noise distribution of the measured data points we could expect with LIFEsim or with Life. We can also use it to calculate yield estimates, as mentioned before, and we can also use it to generate these red modulation curves that can be used to investigate the performance of signal extraction algorithms. In this hands-on session today, we are going to look at these two because we think that this is the most relevant for most of the users of LIFEsim. Okay, before we start with the hands-on session, here are a couple of examples where LIFEsim has been used so far. So we have the paper by Konrad et al. From 2022 and the one from Ale et al. From 2022 as well. They both have used LIFEsim to create noisy input spectra, which they used for later retrievals. And then we also have this example by Angerhausen et al. 2022, who used LIFEsim to investigate the detectability of phosphine in an emission spectrum of a super-Earth. Okay, this brings us to the hands-on session part of this presentation. So, as I mentioned before, we are going to work with a Google Colab file, and this file is quite fully packed. So here's a short overview of what you can expect in this file. We have a first chapter, chapter 0, which just contains the prerequisites. So basically this contains the code to install LIFEsim. Then we have a first chapter, or a second chapter, but with number 1. This contains 2 examples for use case 1, the noisy spectrum generation. And then we have a third chapter dedicated to the yield estimates that contains yet 2 other examples. We are going to start with these 2 examples for the noisy spectrum generation. So in a bit more detail, we're going to start with a short demo, very basic example of how you can actually use LIFEsim. So we will start with a dummy spectrum that is already in units of photons per seconds per meter squared per micron, and then try to generate these noisy spectra that we have already seen before. Then in the second example, you will get the chance to investigate what Life can actually detect. So the question we would ask you is something like this: what observational or instrumental parameters are actually needed to get a statistically significant detection? So we will start with 2 PSG-generated spectra in units of spectral irradiance. So one spectrum corresponds to an Earth twin at 10 parsec, and the other spectrum corresponds also to an Earth twin at 10 parsec, but with a 1,000-fold increase of ozone abundance. We will then use these 2 spectra to generate noisy spectra again, and then calculate the statistical significance of a detection. And then you will get a chance to play around with some input parameters of LIFEsim and see how this impacts the statistical significance you get as a result. Okay, so now I would quickly hand over to Felix, and he will briefly talk about the different input parameters of LIFEsim.
Okay, so hello also from my side. Part of what we did at the life science meeting in Berlin was also to talk about how we can go from higher level mission requirements. So, for example, the need to detect a certain molecule to certain abundance, how we can take this and go to lower level mission requirements. For example, needed wavelength range or something like this. And the question came up, what kind of parameters we need to consider here. So I want to give a very quick recap of the most basic technical requirements or technical parameters that we can set for life and an extension also for LIFEsim. So what we see here is a synthetic planet population generated with Jens Kammerer's PPOP tool. And I plotted all the mostly rocky planets that it spits out over their angular separation, so the separation between the host star and the simulated planet, as well as their contrast at 10 microns, so how much less thin the planet is than the star at 10 micron. And plotted in blue are planets inside the habitable zone, and in the back in gray are planets outside the habitable zone. So next slide, please. Please, next animation. So the first technical requirement that we can think about is the angular separation, and I think we've all seen this argument. So to start cutting into this, population of habitable zone planets, you really need to get to very high angular separations. And usually in single aperture telescopes, even something as large as the European Extremely Large Telescope will not be able to go significantly into this population. So this is why we need these large baselines that life has to give us a large angular separation. And you see, I'm already talking about baselines. So this will something that will come up again later. And then we also talk about the contrast. I think the contrast is not so much relevant here because this is usually fixed by the architecture choice. And in basically all our simulations, the baseline is fixed to be a dual Bracewell nulling beam combiner. So we're not going to talk too much about this, but I do want to talk about the sensitivity. So this is indicated by the color of the blue dots. Sensitivity usually tells you how difficult it is to detect a planet in the absence of a star, so just over the background noise that you have. And it is very difficult to achieve enough sensitivity to detect these planets. So if we put in the next animation, I plotted here the distribution of sensitivities. So, oops, that's gone too far. Over what we currently can reach from the ground, and you can see we're way off, and what James Webb can reach, and this will be similar to what life can reach. So I'm telling you all of this, so now we can go to the next slide, because I think we can basically put our low-level mission requirements that we need to define to move on into 3 boxes. So the first one is the sensitivity box, and the sensitivity is usually defined either by aperture size or by throughput or by integration time or by setting a target signal-to-noise ratio. So changing all of these input parameters will usually just change the sensitivity of the instrument you're simulating. So I invite you here to really think of this in terms of sensitivity. What I mean by this is that, for example, choosing a bigger aperture or integrating for a longer time usually has the same effect. Then the second thing is angular resolution. And this means how close you need to get to your host star, or basically how far away targets can be to still be detectable. And this scales with the maximum baseline. So here the maximum baseline is a parameter that we can play around with to reach targets that are further away or closer. So stars that are further away or planets that are closer to the host star. And the last one is spectrum quality. So this is something that's really on the science team to figure out. Here we're talking about wavelength coverage and spectral resolution, and this is basically defined by what kind of spectral features you want to observe. So at what wavelengths they usually lie, and how detailed we need to observe them. So with what spectral resolution. Yeah, that's it from my side.
Okay, thanks a lot. Then this brings us actually to the hands-on session. So please go to this link. So just enter tinyurl.com/lifesim-tutorial. And if you have a Google account already and are logged in, you should probably see directly the Google Colab file. Otherwise, please log in or quickly create an account. And then once you have opened the Google Colab file, it's very important that you go to .i or a file and then to copy in Drive, speichern, or to save a copy in Drive. If you don't do this, then you edit the, if you even have the permissions, then you edit the main version of this Colab file that also other people can see. So please do this. I'm going to do it as well. Okay, here you can see the Google Colab file. So please go to File, Save Copy in Drive to create your own copy of the Colab. This should then automatically open, so we can close the original. And here we are. Okay, so here you can see a couple of general information, and also you have links to the files that we are going to download in these code boxes below. So if for some reason the downloads don't work, you have the backup files here and can download them manually and then drag them into this file explorer over here. Okay, so let's get started with the prerequisites. So please go to the first code box and execute it. So this will install LIFEsim from pip and also install a version of Spectros that is used for LIFEsim. Okay, it should take a couple of seconds. Okay, you can ignore this error here. Everything is still going to work. Okay, so it seems like everything has worked fine. So then we can start with the first use case, the noisy spectrum generation, and with the first example. So again, we are going to start with a dummy spectrum that doesn't really have a physical significance, but it's already in units of photons per seconds per meter squared per micron. So first of all, we are going to download this dummy data. So please execute the codebox 1a.a. And if everything worked, then sooner or later in this file explorer here, a file named 1a underscore example underscore spectrum should appear. But this might take a while. There it is. Okay. Then in the second step, you can set your simulation variables. So here are the ones that we recommend you to actually play around with. As Felix has mentioned before, there are many others that you can specify, but we really only recommend you to change this if you really know what you're doing. So for example, here we can set the basic scenario. So we have three options for this. We have the baseline scenario, we have a pessimistic and a optimistic scenario. If you set the scenario, then it will automatically set all the parameters corresponding to this scenario. But you can then also, in addition to this automatic setting of your options, set some options manually. For example, if we want to set the spectral resolution to 50, then we can define this here, minimum wavelength, maximum wavelength, and the integration time in seconds. So please execute this box over here. Here we also have some astrophysical parameters. So we are going to input a spectrum, and LIFEsim needs some context information for this spectrum. So we are going to tell it that the planet has a radius of 1 Earth radius, angular separation of 0.1 in arc seconds, distance to the star 10 parsec, star temperature and stellar radius, and finally the exosody level. So once we have executed this box, we can move to the next one where we actually set up our LIFEsim pipeline. So we are going to start by importing LIFEsim and then create the main LIFEsim object, which is called a bus. After this, we can set the scenario. So here we are going to set the baseline scenario from that we have defined above. And then we can also set the manual options. So we're going to set the spectral resolution, the minimum wavelength, and the maximum wavelength. Once this is done, the rest is really formalities. So we're going to create the instrument and add it to the bus. Next, we're going to create the transmission map, add it to the bus, and finally create the different noise sources and add them to the bus. So here we are considering exosody noise, local Soddy noise, and stellar leakage. Once all of this is done, we then need to connect these different modules with this code here. So please execute this code box, and then we can move to the next one. So here we are going to actually import the spectrum into LIFEsim. We're going to do this with the spectrum importer object. So we can create one here. Then we're going to call the doImport method of this object and pass it the path to the text file of the data that we have downloaded before. Now we can also have a quick look at this data. This is simply a text file with 2 columns with the counts in one column and the wavelength in the other column. What is important here as well is that we give the correct units. So we have the wavelength in micron, and as I mentioned before, the counts are in photons per second per meter squared per micron. So once this is imported, we can also have a look at how the spectrum looks. So let's execute this box, and then the spectrum should appear. Then in the next box, we can actually run the simulation. So please execute it. And how we run the simulation is by calling the getSpectrum method of the instrument object. And to this method, we pass the different variables that we have defined above. Okay, now then keep in mind that this method gives us 3 different outputs. It gives us the SNR object, the flux, and the noise. We're going to see how we use them in the next box. So first of all, we also want to plot our original spectrum to this image here below. So we have to rescale it to the amount of bins that we used for our simulation. We can do this with spectras and this code section over here. Then LIFEsim gives us basically the noise distribution that we can expect for our observation. So if we want to generate these random measurement dots that we can expect from this measurement, then we draw here one sample out of this distribution. And finally, the rest is just plotting code. So if you execute this, the same plot appears again, and we end up with the plot that we have seen on the slides before. So here we have the original spectrum as a black line. We have the 1 sigma error bars as shaded gray area, and we have the simulated observation as dots. If we also want to have a look at the SNR we can expect per wavelength bin, we can do this by plotting the first part of the SNR tuple or against the second part of this tuple. Okay, so this should have taught you how to basically use LIFEsim. So now it is your turn to play around with the second example. So again, we have 2 spectra that we have generated with PSG, one of an Earth twin and one of an Earth twin with a 1000-fold increase of ozone. So the steps that we are going to do are basically identical to the one of the first example, with the exception of this statistical significance investigation at the end. So we can execute box number 1 to download the data. This should take a moment, but we can probably already move on. Then we basically extract the relevant columns out of this PSG data using this code box. Okay, and create pandas data frames. Then we can again set our simulation variables and set up the LIFEsim pipeline. Okay, then again, we can import the spectra into LIFEsim. So for this, we have to create 2 spectrum importer objects. And notice that this time the units are no longer photons per second per micron per meter squared, but since we have generated the spectrum PSG in units of spectral irradiance, we can give here watts per meter squared per micron. And if you execute this box, you should arrive at a plot like this. And again, we can run the simulation by calling get spectrum for the different input spectra. And then we do the same steps as above and end up with these two plots. So here in blue, we have the Earth twin spectrum, and in the orange line, which is not very well visible, maybe in this part here, we have the Earth spectrum with increased ozone, 1 sigma area for the Earth twin with increased ozone, and finally the measurement points. And then here we have the difference of these two measured data in units of 1 sigma. And you can see that with the parameters that we have chosen so far, we have pretty low statistical significance. So please maybe stop the video here and play around with the parameters to try and find a strategy to increase this significance here. Okay, once you are done playing around, then we can move to the second chapter of the hands-on session. Let me start the presentation again. So this second session is dedicated to the yield estimates use case. So we again are going to start with a brief demo of what parameter space of exoplanets life can actually detect. And then it is your turn to find out how many of your favorite type of exoplanets life can detect. So for the demo, we are going to start with a PPOP-generated exoplanet population catalog, and then calculate yield estimates and analyze the outputs a bit to create plots like this. So again, Felix has already mentioned PPOP before. PPOP is another Python tool that is separate from LIFEsim that has been developed by Jens Kammerer and is based on Kepler statistics that allows you to generate the exoplanet population catalogs. In the second example of this session, again, you are going to have a look at how many of your favorite exoplanets life can actually detect within 10 parsecs in 20 days. So we start with the same input catalog, calculate yield estimates, and then you can analyze the outputs yourself. And for example, arrive at a statement like this. We can, for example, find any number of super Earth around M stars. Okay, before we do this, two important points. We have also already mentioned the input catalogs, but you are all, also going to use the optimizer in LIFEsim, and Felix is going to say a few words about the optimizer.
Okay, yeah, exactly. So in the blind search phase that Life will likely have to perform, I think it has been well known that, so we have a certain amount of integration time available, likely 2.5 years, and it has to be well known that the way in which we distribute this integration time onto our different targets will influence the scientific outcome of the mission. In particular, it will influence the yield, so how many exoplanets we can find. And here I'm going to maybe take 2 minutes to talk about how we distribute observing time to maximize the number of planets that we find. So the way that we do this is first we have to understand that in the PPOP catalog, we marginalize over input parameters by creating different universes. So this means that we create about 500 different universes. In each universe, we take real stars and distribute or basically sample from Kepler statistics synthetic planets to be positioned around those real stars. And we repeat this process in the other universes around 500 times. And then the optimizer goes and asks every star, how much time would you need, how much integration time would you need to give us a detection of one more exoplanet? And then we build a list of all these stars telling us this, and then we give integration time to the star that returns us the lowest required integration time to produce one more detection. And then we update this list and again give time to the most efficient stars, or the one that requires the least amount of time to get one detection. Then we repeat this process until our 2 years of observing time are used up. And this ensures that we have maximum, that the yield that we reach is maximized. Now, you might wonder whether this is not unfair, because it does require perfect knowledge of the system, right? It requires knowledge of how long you would need to observe to detect the planets, of which you by default don't know that it is there in the real world. The reason why this is still a realistic assumption is because we require that in all 500 different universes, the same amount of integration time is used per star. So this means that we cannot get particularly lucky in one draw, particularly unlucky in another draw. But we do prefer systems that are just generally, where exoplanets are just generally easier to find, and especially exoplanets in the habitable zone. And you can see this in this plot that has been running in the background. So what we see here in the bottom is that the planets which are preferredly observed are usually those which are close by, which makes sense because for those stars, we have the highest sensitivities towards like exoplanets. Yeah, I think this is most I have to say about it. Otherwise, Life Paper 2 also covers part of this.
Okay, very good.
You,
Thanks. Thanks a lot. Okay, so let's move again to the Colab file. And start by downloading the example catalog. Okay, then in the second step, we again can set our simulation variables for the yields. So we execute this box. And then again, set up our LIFEsim pipeline and import the catalog. So the importing is done in this section here. This is really the only part of the code that is different from before. And what we can do, or what we have done here as well, is that we have removed all stars of a certain type that are more than 10 parsecs away from us. Okay, so we can execute this box. And once this is done, we can create the optimizer object of LIFEsim. And finally, run the simulation and save the results. So with this reduced planet population catalog, this should take around 2 minutes or 3. And once this is done, we then save the results as HDF5 files. So if you have done this once and want to reanalyze the results, you can also import them directly using this code section over here. Okay, let's wait a few minutes. Okay, once this code box has finished running, then we can move to the next section and simply have a look at the output catalog. So if you work with pandas data frames, one nice command is the .head method, which simply gives you an overview of the first 5 rows of a data frame, just for you to get an impression of what kind of data your data frame contains. Okay, then here we have 2 example plots that we can now create with this output data. So for example, we can have a look at the number of detections per stellar type within 10 parsecs. So if you execute this box, you get a histogram like this. So we can see that we have mostly detections around M stars and few around K stars and almost none around F and G stars. So here we can clearly see the bias of life towards M star planets. Then we have a second example. You can execute the box of number of habitable zone planets around M stars. So this plot here is only for a single universe. So it is not a mean of of the 5 different universes that are present in this catalog. And this basically tells you the completeness of our detections. So in blue, we have the total of habitable zone planets around M stars, and in orange, we have the detected ones as a function of distance to the star. Okay, this concludes the demo part of the second example. So now it is your turn to have a look at this output data and then try to find the number of exoplanets of your favorite type that life can find. So if you have already executed the first steps of this second part above, then you can skip all of this below. This is simply the same code. And then at this last box here, you can play around with the data frame, have a look at what kind of columns you actually have in your data, and then output the number of planets that fulfill your requirements. Okay, so for my example, I want to output all the habitable zone planets that are approximately or that have approximately Earth radius. So I set the lower limit for an Earth radius of 0.8 and the upper one of 1.2, and I put the habitable flag to true, and out comes 31.8 planets as a mean of these 5 universes. So please play around a bit, and once you have finished playing around, we can come back again to the slides and end with the conclusion. So what we are planning to do next regarding LIFEsim is the development of LIFEsim 2.0. So basically this means we want to have a tool like LIFEsim that also includes systematic instrumental noise. So likely this will require quite big changes to the code base of the current version. So we might end up with a different tool. In any case, we are going to make sure that the transition from LIFEsim to whatever the new tool is going to be is very easy for all its users. So what exactly does this mean for this current version of LIFEsim? It means that it will be maintained, but not actively further developed. So if you have questions, we are always happy to answer them. If you have bugs, we will always try to fix them. And if you have feature requests, we would happily collect them. And maybe if we have student projects, or you have a student project suggestion, then this could also be implemented like this. For us, implementing new features for this version is currently not a priority, but of course, if we have time, we would be happy to do it. So what can you do now if you want to get started with LIFEsim? So either you can just keep using the Google Colab file and adapt it to your needs, or if you want to install LIFEsim locally in your machine, please go to lifesim.readdocs.io for installation instructions. And then finally, if you have any questions, please contact us at this email address here. And then there's nothing left to say except have fun with LIFEsim. Thanks for watching.